Okay, let's look at energy and of the simple harmonic oscillator. We know that the total energy of a system can be written as the total energy K is equal to the sum of the kinetic energy and the potential energy of the system. So we write E as the total energy, and E is equal to K plus U, where K is kinetic energy and U is potential energy. We also initially know that the definition of kinetic energy is just half mv squared, where m is mass in kilograms and v is speed in meters per second. And we also know potential energy can be written as half kx squared, where k is a spring constant, and obviously we are referring to an oscillatory object, and therefore it has a spring constant, and also x would be your displacement. So having defined all these terms, we can go on then to say that if we have an object that oscillates, then we can say that the position x as a function of time can be written as a cosine omega t plus phi, where we know that a is amplitude of the oscillation in meters, t is time, phi is a phase difference or phase angle. Let's use phase angle. And omega is our angular frequency, where we know omega is equal to 2 pi f, where f is our physical frequency. And so we know what x of t is. So we now also know that v of t, the speed as a function of time, can be written as minus omega a sine omega t plus phi. So we can now substitute the value for v of t and x of t into our formulas for kinetic energy and potential energy. And so we will say that substituting x of t and v of t into k equals half mv squared, and u equals half kx squared. We have k, kinetic energy, now being equal to half m, and we'll have omega squared a squared sine squared, and then we'll have omega t plus phi, and then for u we shall have half k, we have a squared cosine squared omega t plus phi. I would like you to substitute these two quantities, x of t and v of t, into the kinetic energy formula and work it out to arrive at k and u as I have here. So now the total energy E, which we said was equal to kinetic plus potential energy, can now be written as E equals half m omega squared a squared sine squared omega t plus phi plus half k a squared cosine squared omega t plus phi. Note that k and u are either positive quantities or zero. We also know that omega squared is equal to k over m. Therefore, we can say k is equal to m omega squared. And by having that, we can replace, we can make a substitution. So we substitute m omega squared into the kinetic energy formula. And my notation here, I guess, I think I'm using a notation which is not very good because I'm using the same k for different things. So let me write it this way. Let me make sure that you know that k that I'm referring to in your in this formula here is different. So in the potential energy, let's write it this way. K, let's do this way. So let's make sure that we make the system convenient for us. This is Ke, so that we can differentiate it from K. So we are talking of kinetic energy Ke. So I'll just make sure that this is always Ke, so that we don't get that mixed up with the spring constant K. So we can substitute m omega squared into the kinetic energy formula above to get Ke equals half K A squared, and then we shall have sine squared omega t plus phi, and then our potential energy obviously is the same. U was equal to half K A squared cosine squared omega t plus phi, and the total energy E is the sum of these two. And so we can say that, let's write half K A squared on the outside and put sine squared omega t plus phi plus cosine squared omega t plus phi on the inside, and we'll use one of our trigonometric identities. So we know that sine squared theta plus cosine squared theta is equal to 1, and by adding the phase angles, this will not make any difference. It doesn't change when you add phase angles, so we can say E is equal to half K A squared, where the term in parentheses or in the square brackets is equal to 1. Okay, so now we have our total energy for a simple harmonic oscillator. So this tells us that the total energy of the harmonic oscillator is a constant of the motion. I'll write simple harmonic oscillator as SHO. Let's write it as SHO. Okay, so what I just wrote was that the total mechanical energy of a simple harmonic oscillator is a constant of the motion and is proportional to the square of the amplitude. That's our final ultimate result. So when we consider a system that is in oscillatory motion, for example, if we think of a spring at the end of, if you think of a block at the end of a spring, as the block is oscillating, when it reaches its maximum potential energy, where the spring is either fully extended or fully compressed, at those points it comes to a stop, and so the velocity or the speed at that point will be 0, which means that all the total energy would be just the potential energy, because the displacement x will be at the maximum. And so we can say that the total mechanical energy is equal to maximum potential energy stored in a spring when the displacement x is equal to plus or minus the amplitude a, because at maximum amplitude of displacement, speed v is equal to 0. So there is no kinetic energy at those points. And then we can also say that at the equilibrium position, the displacement x is equal to 0. So at those points, or at these points, actually at this point, not these, at this point, v is maximum. So the total energy of the system is kinetic energy. We can plot variations of kinetic energy and potential energy, variations of kinetic energy and potential energy. We make potential energy, I'm using the letter U for that. Variations of kinetic energy and potential energy in the next page. So let's say, for example, we want to plot a graph of kinetic energy and potential energy as a function of time. We can plot one this way. So let's plot that as our potential energy. This is U. And then we can plot kinetic energy this way. Actually, let's do it this way. Let's just make that. So this would be your kinetic energy. In this case, we are saying that the phase angle is equal to 0. So we're just plotting them without the phase. And this is your maximum energy. And then we can also plot the variation of kinetic and potential energy with respect to amplitude. So let's plot that here. Well, let's say this is positive amplitude, negative amplitude, and we have kinetic energy and potential energy here. And again, our potential energy is going to be the broken line. So let's go this way. And then we'll plot kinetic energy this way. Okay, so this gives us the amplitudes. This is A, and that's minus A. So let's put that in the right place. So we can also get a velocity. We can also get a velocity v at some arbitrary position by solving for v in the total energy. So we had our total energy E to be equal to half k, and we had half k A squared, and this can be written as half mv squared plus half k x squared. So the total energy E, which is equal to half k A squared, is equal to half mv squared plus half k x squared. So at this point, we can solve for v in this formula. So we can say that half mv squared is equal to half k A squared minus half k x squared. You can remove the halves and divide by m, and you end up with v equals k over m. And then we're going to have a squared minus x squared. Take the square root of that, you have v equals the square root of k divided by m, and you have a squared minus x squared. So this gives us the formula for the speed at some arbitrary point in the motion. If you like, you can replace k over m by omega, or in this case, k over m would be equal to omega squared, and we'll take the square root of that. So you have v equals omega, and in the square root you have a squared minus x squared. Let's add here that we took the square root, so we're taking plus minus on this, so it's either the positive or the negative speed. Okay, so this is the end of the section on the energy of a simple harmonic oscillator. We will go on to something else next.